Hi everyone, we are getting ready to start our downward slide of physics. We are going to begin our sections on rotation. So at this point, basically what we are going to do is we are going to take everything that we have learned with respect to linear motion so far this year, since August, and we are going to look at what would be the similar behavior if we were then rotating about an axis. So let's get started. So before we get too far, let's recognize that we are going to be looking primarily about rigid bodies. So that is, as you know, a body that is very fixed. The positions are fixed. They are not moving, shall we say. So if you think about video games, that would be like you have the character and the character turns, but the arms don't move. They're very fixed into position. So when we start looking at this, so a translation, by definition here, a translation is when the object moves along a straight line or curve. So that is a translation. So this is our linear motion. Now, rotational motion, we have an object turning about an axis. And highly original, we call this axis the axis of rotation. Now, if that axis does not move, we call that a fixed axis. I know, hugely surprising here. So, what are we going to look at first? Well, first things first, when we start looking at angular position, angular velocity, angular acceleration, when we start looking at that rotational motion, we need to look at what it's with reference to. So let's start with some of the basics here. We have a circle. So that circle, we would say our axis of rotation, right along the center. So we would be, let's pretend we are particles spinning along out here on the edge of that circle. So this distance is r. Now, if we travel through a given distance as we go through time, we'll say we're going to travel this distance s here. Well, how do we find that distance s? Realizing, of course, that we have traveled some angle theta. It feels like we're going back to geometry class. Well, you may remember that 2 pi r is our circumference. Yes. You may also remember going from math class that if we look on the edge of the circle and we take a string, the length of the radius, and we map it around the edge of the circle and we lay it out, the angle that it covers is called 1 radian. So that would be the angle that it covers. So for the full circumference, so how are we going to find this little distance s? Well, it's going to be a piece of that full circumference. So if I took that full circumference times a ratio of the angle, so theta, the total radians in a circle is 2 pi radians. So what you get is you have 2 pi r times theta over 2 pi. So what we end up with is this relationship that our linear distance that we have traveled along the edge of the circle is equal to r, the radius of the circle, times theta, our angle. Now this theta is in radians. So in physics, that angular distance has a unit of radians. And yes, we do use theta. So how am I going to find the angular velocity from this? Well, what you may remember is that velocity is the time derivative of the position function. So in this case, if we're using s for our position, not for speed, for our position, then that means we are looking at the derivative with respect to time of r times theta. Well, r is our radius of our circle. That's not changing. So we're going to have r times d theta dt. Well, that is the rate of change of the angular distance. That right here is our angular velocity. Now, our angular velocity units are going to be radians per second. That's our typical SI unit. But then it goes, okay, we have V for so many things. What letter do we use? We actually use the Greek letter omega, lowercase. It's like a little script W. And that is our angular velocity. So we get that the linear velocity, the tangential linear velocity, is going to equal r omega. So I have this connection piece. I have this connection piece. Well, but we have position, we have velocity. Where are we going to go next? If you've guessed acceleration, you are right. So if you remember right, acceleration is the rate of change of velocity with respect to time. So it means it's going to be the derivative with respect to time of r omega. Now our radius of our circle, our rotational path, not changing. So it's going to be r times d omega dt. This is the time rate of change of the angular velocity, which means that we are going to be looking at the angular acceleration. And the angular acceleration, it does have units of radians per second squared. So what do we abbreviate that with? We use the Greek letter alpha. Now, you may be saying, why do we change our variables? If we change our variables, we are very clear whether we are looking at linear motion or rotational motion, because there are times where these two worlds will collide and we'll be using both pieces at the same time. Not right this second. So, our basic interconnections, if you look at it, is that our linear piece is the radius. We are out from our axis of rotation times our rotational piece. So that's going to be our keys to the kingdom as we move through our rotational world. So going back to our note guide, that is where this equation for the angular position, where theta is equal to our distance around the edge of the circle divided by r. Our angular displacement is going to be the change in theta over the, and then for our angular velocity, we're going to have change in theta over change in time. We did that with derivatives, looking for the instantaneous. So of course our average, we're still using delta. Our instantaneous, we're going to be using derivatives. If we're looking at angular speed, it's just going to be the magnitude of those angular velocities. So what can we do? So we have a child's top is spun. We have an angular acceleration right here, 5t cubed minus 4t. At t equals 0, the top has an angular velocity of 5 radians per second. So that is an initial angular velocity. And it says that we are at an angular position, theta equals 2 radians. So theta naught is equal to 2 radians. Now, I need to find an expression for the angular velocity. Now, I just said that the angular acceleration is the derivative of the angular velocity with respect to time. So that means that my angular velocity is going to be connected to the integral of my angular acceleration with respect to time. Now, I don't have limits of integration, so I have to add my constant of integration, which is my initial velocity. So that means I'm going to have 5 plus the integral. I have 5t cubed minus 4t dt. Now, this we're going to be using power rule. So with integral, we're going to raise it up a power. So it's going to be t to the 4th. We're going to divide by my new power, which is 4. So here we're going to raise it up by 1 power. So it's going to be t squared. And we're going to divide by my new power, which is 2. So basic simplification for my angular velocity function with respect to time. That's going to be 5 plus 5/4, or 1.25 t to the 4th minus 2 t squared. So that is part A, checked off. Part B, I need to know an expression for the angular position. So what do we remember? We remember that the angular velocity is the derivative of the angular position with respect to time. That means that theta is going to be connected to the integral of the angular velocity with respect to time. Now, I do have to, since I do not have limits, add my constant of integration, my initial value. So this is going to be 2 radians plus the integral. I'm going to have 5 plus 5/4 t to the 4th minus 2t squared dt. Here's where being extra cautious pays off, because if you're not careful here to include this constant of integration, you're going to be missing an entire term over here. So this is going to become 2 plus 5t plus 5/4 t to the 5th times 1/5, because I have to divide by my new power. Notice that those 5s are going to cancel. I'm going to have 2. T is now going to be cubed. I need to divide by 3. So this is going to become 2 plus 5t plus 1/4 t to the 5th power minus 2/3 t cubed. That is my angular position function. So I'm going to pause this, and we're going to come back for some more here in just a little bit.